All right, so we are with Frank McSherry. He is a senior researcher from MSR in Silicon Valley, or Mountain View, I guess. I think they're one and the same, right?
Yeah, absolutely.
So you were working on a really interesting project called Naiad, which is tangentially related to Dryad, something we covered pretty extensively on Channel 9 with one of your co-scientists.
Right, Michael Izzard.
Exactly. And that was a fun conversation. It's all about data parallelization, right?
Yep.
What is Naiad?
So Naiad is sort of where we went after doing the work with Dryad and Dryad Link. Dryad Link took Dryad, data parallel computation, tried to make it a bit more accessible for people who are familiar with using C#, Visual Studio. They wanted to write programs that look like Link as opposed to it's horrible scripts for firing up Hadoop jobs and stuff like that. So we gave them all the good features of a integrated development environment, type safety, all sorts of good stuff. Naiad was sort of the next step. We got a lot of people asking us for features in Dryad and Dryad Link, sort of system-level structural features, like I want to be able to get early results out of my computation, or I want to be able to do iterative computation, which is something that Dryad didn't support. It only does directed acyclic data flow graphs.
Okay.
And so we started thinking about how to go about doing this. And actually, initially, we started taking Dryad and trying to hammer on Dryad and bang it into a shape that would allow some of these features. But fundamentally, things didn't really seem to be working out. It was a little annoying and difficult. And so we sat down and we thought for a little bit. And we thought, how could we actually do this if we had to start over from scratch? And after a bunch of thinking, we came up with some neat bits of math related to how you do data parallel computation that turned out to be much more general than just getting early results out or just doing loops. It ends up this neat system that has all these nifty composable properties. You can actually do them all at once, which is unlike anything that we're aware of from the research community before. And
interesting. So can you, like, at a high level, can you kind of explain sort of the math behind it? We don't have to get into the equations and weird symbols that you guys like to do. That's already in the paper. People can read that.
Absolutely.
If they want to geek out on the math.
So, so the general gist of this sort of thing is, so back with Dryad and Dryad Link, and lots of big data systems, you have these collections of data, which you can imagine, like a terabyte or so of data, that you tell the computer to pick up and process in a certain way. Computer picks up the terabytes of data, and if you're running something like a group by or a join or something like that, it fires a key function across all the records, figures out where to send all of the records, and it goes and processes all of these things. And that was good enough for that type of work. What people have realized, and they've certainly realized this a while ago, 20 years ago, the database community was already doing incremental computation. So they would say it's silly to pick up the terabyte again to do a join if only 5 records have changed. Let's put the new 5 records in, see what they're supposed to match in that join, and just produce the new records out on the other end. Same thing with loops, it turns out. People have also realized approximately 20 years ago that if you're going to do a loop with big data computation, you don't really need to do the whole computation each time. You should just figure out what's changed at the end of the loop, push those changes into the beginning of the loop again, and push them through again, as if someone had changed your data, your input from an exogenous source. So these ideas were already out there, and we could have just made Naiad be a clone of these ideas, just implemented that, and people probably would have been pretty happy. It would have done the cool things that people had asked for. But there's this neat twist with Naiad that is what makes it actually new, interesting research, which is that rather than having these collections, which in an incremental setting sort of vary from the first collection to the second collection to the third collection, this linear total order. Right? There's always the most recent one, and it's always just a diff off of the previous one. These collections can actually change in multiple independent dimensions at once. And this allows really cool stuff to happen. Particularly, you can incrementally update the input to an iterative computation. So you have these 2 dimensions, one of them being the sort of the epoch or batch of input data that your computation is taking. The other dimension is the iteration around the loop inside the computation. And as far as we're aware, most of the previous techniques for doing this type of computation essentially have to restart the loop each time new data shows up. There's not really a lot you can use from the previous time through, whereas we can actually push changes through iterative computations. There's one of the examples that we might get to of doing this and getting results back in millisecond timescales, having done big iterative graph analyses on large social networks and stuff.
That's amazing.
So
why don't we see what this looks like? Because a lot of people watching this, of course, are developers. They're used to system.link, and those query operators and stuff. Let's see what you've done.
So it's very, very similar to Link. We've definitely tried to make it be as accessible as possible. And in some cases, we've succeeded. In others, there's some things we couldn't really hide. But the general idea is that you have a Naiad DLL that you link in, and you just fire up using Naiad, and you have access to the Naiad namespace, which has a few useful things in it to get you started. one of them, and I should say this program is one of several programs in an example download that we have. It's actually driven by a main method in a different file. I'm just not going to show you that for the moment. So some things, we're going to have an execute rather than a main, that sort of thing. But the idea is that you have, initially everything starts off of this Naiad configuration file. This tells Naiad how you want it to run. Do you want to run it on remote machines? Do you want to run it locally? We're going to run it locally here. You spin up a Naiad controller, and this is the thing responsible for making sure all the work gets done in a Naiad computation. Typically, you just have one of these per computation. If you're using something like the reactive framework, this might be analogous to a scheduler.
Okay.
So you spin up one of these folks, and it controls all of your resources and makes sure stuff happens. Then, and this little bit here is the program. It's going to be really simple. You ask the controller to make a new input for you. This is a lot like asking for a new iObservable, something like that. This is a new place that you can put input data that you're going to base your computation off of. You're going to attach a few things to this and build your data flow from this root. So we've tried to mimic a lot of the link patterns. In this case, we're going to take this text input that's meant to accept strings and subject strings to further computation. We're going to take this and we're going to hit it with a select many function, a lot like in link. So this is something that you hit each record that it sees with a function, and it produces a list of output records. In this case, we're just going to split lines of text into multiple individual words.
Okay.
We then throw a count at it. This is a slight deviation from link. So count in link, if all y'all are familiar with that, is sort of a terminal operation. It returns an integer to your program. It interrupts the data flow. Right? So you can't really continue further data flow off of that. The count that we've done here is sort of a data flow friendly count. It produces records that are still inside a collection.
Okay.
So it's like doing group by and then a count, essentially. For each of the groups, it tells you how many things had that particular key. And that's exactly what we want to do in this. This is a word counting, I should have said, example. We're going to take all of these words, we're going to count them up, and we're going to say how many times have you seen a particular string. All we're going to do when we do the count is stick together the key, which is the word we had in mind, with the count, which is the number. So nothing too surprising. And then we subscribe to it in the same way that you would subscribe in the reactive framework. So this is something that's going to get called every time a new record gets produced from the count. And we've scribbled down a callback here that's going to print out all of the stuff that happens to get handed back to us. And that's the Naiad program.
Nice.
So there's a little bit more program, of course. There's the C# side of we have to get the data from the console. And
but it's not related to Naiad.
Well, it's not specific. Certainly you want to have it, because otherwise you haven't actually given Naiad any input yet. So that's no good. But it's not at all complicated. So as you can just see it here, it just starts pulling lines of text off of the console, and every time you give it a line, it stuffs it right into the input of the computation. Ideally, exactly as would happen with the reactive framework, with an iObserver and iObservables. So the pattern, we hope, is going to be familiar to a lot of people. The thing that we're imagining is going to be different is that the performance you're going to see out of this, the scalability, the ability to distribute across clusters and do exciting things like these iterative computations will be different. But just to give a sense, let me run this. And this is the console.write line that we started there. It just wants me to enter some lines of text, and I will say things like hello world and press enter. And we get some output back, and this is the thing that's different about Naiad as compared to the reactive framework, the iObservables, is it is going to show us records. So hello:1 is one of the records we might expect to see. That's the count for the word. It's going to show us these records with a number after them. So they're not just records that we're getting output. There's actually, what they are is they're telling us the change in the frequency of that record. So this is saying that previously, hello world had some frequency in the data, 0. In fact, it didn't exist in the data set. Now it's here, and it's got a one higher frequency than it used to have. So there's one copy of that record now in the data set. If I type something like hello, this makes it a little weirder, you see a -1. So what's happened here is that the record hello:1 has disappeared from the data set now. There's no longer a record we want to show in the output. Instead, there's hello:2, which is now the new correct count for all of these things. In the reactive framework, this is a little complicated because you can't really take records back, right? I mean, you show someone something, and you've shown it to them now, and you have a sequence that's meant to grow indefinitely. An important part of Naiad is the ability to correct previous outputs that you've transmitted, and it's part of both the input to the system. So if I had changed the program a little, I could take back inputs. I could do a subtraction of world, for example, and undo that, and it would tell me, world:1 has just gone away. But all of the internal aspects of Naiad, it's really important to have these pluses and minuses, the ability to undo an aggregation, particularly in this case when the correct answer 1 has changed to 2. You want to be able to take that back.
Sure.
So this is not too mysterious. This app is meant to be incredibly simple, so it's not mind-bending. You can play with it indefinitely, but it gets boring pretty quick.
Yeah.
The main
and Naiad's not really doing much work. I mean,
no. Behind
like,
the scenes,
whatever,
it's just hanging out, and it's put
Yeah.
these terms into an index that have a count next to them. And each time you throw a new word at it, it looks them up in the index, bumps their count,
Sure.
and does the appropriate outgoing logic.
Okay.
So pretty simple, and the intent is to try to convince people that this is actually an easy system to get started with, at least.
Sure.
I have another example that I
Okay.
can throw up,
Great.
which is a slightly more complicated one. Let me change the size here too.
150.
Yeah. So this is a connected components computation. Connected components is a graph algorithm, I guess I would say. I mean, it's a decomposition of a graph, like a social network, into these disjoint, of the vertices into disjoint regions so that everyone within a region can reach anyone else.
Mm-hmm.
And it's interesting if you have a social network, what are the connected components, who actually interacts with whom, and that sort of thing.
So connected components could be groups of friends. Or
Absolutely. Well, there's a
groups.
particular mathematical definition that
Okay.
is not only groups of friends, but all the people that they can reach, all the people that they interact with, add out to an arbitrary limit. And actually, that arbitrary limit's the complicated part. So in a standard data parallel setting, if you just said go one hop out or something like that, they're fine with that. You can write that in something like Dryad link. Just one step is good, but in this connected components computation, you have to go out an unbounded number of steps. You don't really know how big it's going to be. You could put 100 in there, but you'd be wasting your time if 100 was too big, and you'd be wrong if 100 was too small.
Sure.
So you'd like to be able to do this iterative computation that we were talking about before. Start doing your work, and if things change, if the ability, the set of people you can reach grows a little bit, you do a little bit more work based on the new people you can reach. And you don't redo the work based on the people you already know you can reach.
Got it.
So we're going to do this particular example, which is going to be a much bigger scale. We're going to throw together a big random graph, and I want to say it's on the order of 10 million nodes or so that we're going to fire in here. We're going to put a bunch of edges in, about 5 million, a little bit more. This is the right number to make it an interesting computation. Turns out otherwise it's too easy. And then, like before, we set up a controller the same way we would before. We prep an input which is going to have these pairs of integers. That's how we're going to describe our graph. Each edge is going to be a source and a destination integer. Get a stopwatch ready, but then we fire up our connected components computation. This is an extension method that I'll possibly sneak us up to in just a moment. But it goes off and it returns a bunch of int pairs that describe for each vertex in the graph what is the label of the component they belong to. And everyone in the same component should have the same label. And then we do a little bit of counting here so that we can report how many components are there of each size, essentially what we're looking at. As these results come out, it'll tell us how long it took. Remember that when we actually start running it, because otherwise it might be a little mysterious to see what's actually going on. But with the exception of this extension method, which I'll get to, that's basically the program. We push in the data down here, so edges on next, and you can sort of see this is hinting a little bit the distributed nature. So if the controller's process ID is equal to 0, put in the data. Otherwise, don't put in anything. This is already looking forward a little bit to running this on multiple computers. And if you run on multiple computers, you don't want each process to put in the entire data set. Again, you just want one person to put it in. They'll take care of distributing it out for you.
Interesting.
So all of these programs, the same program runs on your laptop as runs on the cluster. It's meant to be very nice that way. You're not meant to get too confused about, wow, distributing stuff across compute clusters is hard. It's supposed to be easy if we've done our job right. The program is going to continue after we stick all the data in and allow us to start doing updates to it. So there's this weird iterative computation. We're going to start changing some of the inputs a little bit. And we'll look at the answers and see how they've changed, but the timing is going to be the most interesting thing. So how long it takes to actually do an update to this big computation is going to be interesting. Let me just say a little bit about what actually happened in this connected components computation. This isn't the one I showed you. The one I showed you is connected components fast, but this is a lot easier to understand what's going on here. The gist basically is that we're going to take a bunch of labels at each vertex and we're going to push them through the graph. Everyone's going to keep track of the smallest label they've ever seen. And the idea is that everyone within some connected component, reachable from everyone else, is eventually going to take the label of the smallest node present in that component. Basically, they'll all stabilize at the same value. But to do that, so we need to start with some labels, and we need to run this iterative algorithm that sort of propagates this value along. And that's this propagate min feller here that is actually pretty easy. It's a little, you can sort of pause it maybe and go through this in your brain, or check out the download.
Yes.
The code's in there. But it turns out it's all just link stuff with a new fancy fixed point method, but otherwise doing joins, concats, mins, nothing too weird. So I'm just going to fire it up.
Okay.
No, I'm not going to, sorry, I need to tell it to start connecting components instead, sorry. There, now I'll fire it up. So it's going to go off and it's warning me that it's going to compute these connecting components on a big graph. I made it pretty big so that it takes a little while and we don't just get the answer immediately. It should be just a few seconds, I hope, unless I've screwed this up. The number of nodes we're looking at is 10 million or so. That's pretty modest for a laptop. You can definitely get bigger than that. Though Naiad is constrained by the amount of memory, essentially. It likes to keep stuff around in memory so that it can quickly get back to things when things have changed. Yeah, it's going to be fine. There we go.
There we go.
So, so what it's printed out for us is for each of the sizes of components here, 2, 3, 4, 5. How many of those components did we find in the graph? And the labels were chosen in such a way that there's a really big, exciting one at the end. So there's a lot of folks that are of medium size up to 600-ish or so. And then there's one fellow who's about 2 million or so vertices. So
wow.
A lot of computation needed to go on to actually identify all of those people and only those people. But the fun thing now is each time I hit enter, it's going to take an edge in the original graph and rewire it to some random new edge, basically. And it's going to tell me how long it took. And in this case, it took 36 milliseconds to push that entire computation through that Dataflow graph, through the iterative propagate until terminated thing. And it's telling me what's happened here. So one of the components of size 5 turned into one of size 6, and one of the components of size 346 turned into 345. And you can do this as much as you like. All of these times are in the, let's say, tens of milliseconds tops, and they're absolutely updating correctly all of the information about how big are these components.
Let's talk about that. Right?
Yeah.
So I mean, it's impressive that it's so fast.
Hooray! Excellent.
But I mean, in some sense, you have this giant graph that you've created, right?
Yes.
And I think what we should do is talk a little bit more about these iterative computations, or this sort of, because when you pressed enter, a random thing happened, but it wasn't a whole compute again.
That's
right?
absolutely
it was
correct.
Just a little.
Right. So what Naiad is good at doing is keeping track of essentially what are the dependencies in the computation. So when I take an edge out, for example, Naiad is very aware how that edge, because we program everything declaratively, how that edge interacts with the computation. It remembers what got propagated along that edge. And it knows once that edge is gone, I need to undo that propagation. I need to tell people at the other edge, other end of that edge, you don't have this label anymore. I changed my mind. Or at least the frequency of that label has gone down by 1. Someone else might have told you it's okay to have this label, but not this edge anymore. And those consequences will carry on. They'll ripple forward. That vertex might say, ooh, I shouldn't have told the next guy downstream that I had that label. And Naiad will sort this out, but it'll stay totally away from the part of the graph that hasn't changed. So if nothing's going on in one big, huge chunk of the graph, in most cases, nothing's going on in the graph, no computation will occur. It doesn't even bother to check it to see if nothing has changed. It just knows, essentially because this is all push, we've been told what needs to be worked on. Right? Someone has said, this is the particular edge that needs to be changed. So we just do that work. And we avoid producing any spurious, reconsider the whole graph or anything like that. So this in principle could be taking milliseconds, arbitrarily large scales. You put a terabyte of memory in a computer and run this thing on it, it will still take milliseconds.
So now when you think about connected graphs of information, it could be that at some point something changes that should be reflected across the whole graph. So call it the God change
Sure.
or something massive. How does Naiad understand that?
It understands that, and it will do all that work.
Okay.
So if you have two big parts of the graph and there's one edge that goes between the two of them, the presence of that edge is really important for the computation. If you take that edge and sort of take it out, put it back in, take it out, put it back in, you're going to annoy Naiad, and it's going to do a lot of work. And that particular update isn't going to take milliseconds, right?
Sure.
It's actually going to go and not only compute the right answer for you, which is good, but it's going to leave the system in a state that you can still do these incremental updates afterwards. So it's going to need to update all of its breadcrumbs as well.
Wow.
So the size that I chose for the number of edges is actually the right size to leave the graph in a sort of very tenuously connected state. If you put a lot of edges in, everyone's just really well connected, and it doesn't matter if you add or remove edges, everyone's still connected. And if you don't put enough edges in, no one's connected, so it doesn't really matter if there's no carry-on effects from moving these edges. So this particular edge density is the one that actually produces interesting results. Of course, I haven't flattened the entire screen with updated output, but you could certainly do that. Naiad would actually figure out the right answer for you. You just might be a little disappointed.
So, and I think what we should do now is like come down just a little bit from, and this is very understandable theory, by the way. So I think everybody out there is, should be clear on this, especially if the big dummy over here is. So what I'll say is this: let's move into a world or a situation where we talk about, let's apply this to a real-world problem.
Sure.
And that will also help us understand where it's really useful.
Excellent. What luck. It's almost as if we had coordinated on this. So the final demo-y thing that I have for you is, if I can see this here, a Twitter trace that we have. And we've actually built up a slightly more interesting, more complicated program off of a Twitter trace that we've taken. And we're going to feed Twitter data at this computation in real time, basically. And we're going to try to watch some real-time analytics. Sorry, in fact, it's actually going to be 5x real time. So just to show you that it's actually capable, we're going to, let's see if I can do this properly. There you go. So what it does do, it takes to make the demo actually interactive, we load up the trace beforehand. We don't actually have Twitter on the line handing us data, so that does take a little bit of time. And I have to admit, the demo is written by someone other than me. It's written by Derek Murray, a coworker.
Okay.
And it's very possible that I'm not going to drive it brilliantly.
That's fine. I think it'll show. It's good to actually have a concrete. That's the great thing about UI, right?
It definitely ends up looking pretty when you see it. So let me close this and restart it. Actually, so there's two applications that are going on now. One of them is the actual computation, which is this Naiad program that we've written that goes and thinks about things like tweet histograms, and there we go. So let me tell you what all these things are. So the bar at the bottom is a timeline of about 2 hours of tweets that we've loaded up. Fits nicely in my laptop. And we have a little slider across it, which is a 30-minute time period, and we're going to start scrubbing the slider around and watching statistics change.
Okay.
What we're showing up here is the most popular tweets, hashtags in all of the tweets. So we've essentially just done a count, basically, by the same way that we did with the word counts. And then we've kept the top 10 or so. I think they're running over there a little bit. On the right-hand side, we have a graph, and these are the large, strongly connected components in the graph defined by mentions in Twitter. So if you tweet at someone, we're going to put an edge in the graph from you to them. And this is actually the strongly connected component structure. So it's going to be directed edges going between different groups there. And there's a few fun stories to tell if I can find them. But let me just start it playing. What you see in the lower left-hand corner is a little green and yellow light. When it's green, Naiad's doing no work, and it's just hanging out waiting for the next second to tick. And it's ticking along. These are counting seconds. So it's doing 5 seconds of Twitter time for every 1 second of real time.
Okay.
Just to give you a sense for the fact that it can move around. And in fact, it's updating all of these counts, call it in real time, second by second. Updating the strongly connected component structure, which if I were to show you the code would cause a substantial amount of anxiety. It's a doubly nested fixed point computation that has all sorts of, basically our tech demo in terms of algorithms. It's about as clever as we could get.
Great.
And this, I want to say it pauses real soon, and there's a little story about the Giants, but no, the Yankees. Sorry, the Yankees and the Cardinals. Here we are. So if I can find them in here. There we go. So we have the Yankees, and we have also the Cards. And apparently, around this time, in the tweet trace, they had a nice significant game. And so there's a whole bunch of people talking about the Yankees, talking at the Cardinals people. So presumably, the Yankees did something relatively impressive that the Cardinals people needed to hear about.
Sure.
But so this is just an example application. I mean, it's very pretty, and the prettiness has nothing to do with Naiad.
Sure.
But the ability to throw up sort of real-time analytics-y computations, and had we just attached this to the Twitter stream, you'd be seeing what's going on right now, which is potentially really exciting. We have a sort of historical trace. We're not actually social scientists, so we don't really know what to look for either.
Sure,
we're systems designers and stuff. But you can imagine that lots of people out there, all sorts of people watching at home, will be able to take these tools and do really cool things with them.
Well, absolutely. I mean, one of the things we hear a lot about these days, we're in the land of buzzwords, is big data, right? I mean, one of the things you want to understand about all this ambient data is another way to look at it. It's just so much data everywhere, so many edges, as you would, so many connections. This is the kind of technology that could be used to help us understand what the hell's really going on.
Right. So definitely being able to take these big piles of data and work with them interactively, right? If you have to wait an hour to get the answers back to your question, it's going to take you a while to actually find the right question, right? You're going to have to iterate for a while, whereas if you can just scrub the little slider around or tweak the questions you want to ask and interactively get these sorts of answers back, I think we hope that this is going to lead people to understand their big piles of data a lot better, do more clever things with them, and provide better services.
Now, I mean, if you think about it, if you look at Facebook, which is sort of the world's biggest marketing experiment, certainly something like this could be exceptionally useful. They're probably using Hadoop or something like that to, I know they actually are doing machine learning actually to understand what's going on. This could be useful in machine learning as well.
Absolutely. So you would imagine, I mean, a lot of these iterative algorithms, for example, this is how machine learning works, is you take some properties, some model that you're trying to learn about your data, and you iteratively improve it. You sort of go around these loops and keep trying to improve it until things stop changing. And this is absolutely critically important for all sorts of, Facebook certainly, lots of advertising that they try to do, for example. They want to figure out what are hot trending topics and who wants to see what based on the current conversations that are going on within Facebook. In principle, very exciting. The stuff they've told us about, the research community, is that they're using Hive and doing these sort of batch jobs. And they do what a lot of people do, which is they try to reduce the data down a bunch first, and then the batch jobs are a little bit more efficient because they've distilled things down to aggregates first. But this makes a really complicated workflow. You got to go re-aggregate everything again, and it's a bit of a nuisance. And ideally, you just have one solution now. I mean, that's the hope, at least. We're still, of course, engineering stuff, but.
But the thing that's also interesting here, I mean, is that in some sense, this is mathematical. This is based on math. So the particular language and tool set you happen to implement it in is sort of orthogonal. This could be implemented in the tools that they actually want to use. It's the math that matters.
Absolutely. I mean, you'd like something that has an interface that's rich enough to capture these things. So for example, the reactive framework is nice because it has things like on, next, and subscribe.
Yes.
These are things that we'd want to have, and it's less clear that. I mean, Hive has sort of you can update tables. I think you can update tables. There's some things even that in SQL that you can't do very easily in a lot of these languages. But you'd really like to be able to have this sort of programmatic access to the computation, the whole data flow. C# is a nice fit for that. You could totally do it in other languages.
Well, I was just saying from the standpoint of people who are running, server infrastructure that doesn't support .NET.
Oh no, yeah, they don't need to shift their stack or anything. Someone would need to actually go and take the Naiad smarts and make that work on their.
Sure.
So your Naiad wasn't, 30 lines of code or something.
But anyway, it's beautiful. Look, Link in C# is amazing. This is
excellent. Well
very
said.
simple to use. The next question I would ask, I mean, I'm sort of wondering if you've used RX in your implementation.
So we haven't, which isn't to say that we couldn't. We just happen to, a lot of the funny mathy bits, like the multiple dimensions and stuff, are very deeply involved in the scheduler and a lot of the resource management that goes on. And if we were to use something like RX, we'd really need to rip it open and get our fingers in there. And it's a little tricky when you're doing prototype code that you're not sure is really going to work out in the first place. Trying to work around, well-engineered and sort of bolted down bits of code can be a little tricky. It's nice to be able to just open it up and say, it's not working, let me put my finger on this, and we'll see what happens. So.
Great. So who's using this? Like you guys, I would imagine you have some scientists that are using this to blast through data sets?
So that's actually where we're going next with it. So we've gotten it to a point, we just had a code release 2 days ago. And our goal now is to start to find people who actually want to use this in Force. We've been using it for a lot of little sort of toy projects like this, little tech demos. A lot of people have come to us and said, I really want something like this. And we're trying to make this link now where we go back to them and say, OK, we've got it. What did we do wrong? Or does it just work perfectly for you? And we can iterate at this point on it. But it's a little, one of the big differences, I guess, between Naiad and Dryad Link is that the selling point for Naiad is this interactivity. So a lot of the scientists were very familiar with, the research scientists. Yeah, interactivity is fine, but it's not really what they want to produce some charts for their papers. And being able to press go on a MapReduce job or on a Dryad Link job is good enough for them. Whereas what's great about Naiad is interactivity for people who are actually trying to develop services, things that need to stay live and interactive. This is sort of the sweet spot for Naiad, and we're not sitting in the same building as these people necessarily. So all the researchers we know, we love them. But for paper writing, Naiad may or may not be the single best tool. It's not its selling point.
That's great. So I mean, I really kind of want to talk about that real briefly as we close here. I mean, we've in some sense, computation as a service is something that we don't talk enough about in terms of cloud computing, right?
Sure.
It's as a scientist who doesn't want to. You think about people who don't want to manage their own IT infrastructure. I guarantee you, scientists and people who need to get numbers out of giant amount of data are among those. And so you want to send up a request to do some sort of computation, and then be able to, as you mentioned, interact with it when you start getting some of the results back without having to recalculate the whole thing again, so that you kind of can help know where it's going and see what trajectory you're on. So you mentioned this would be useful for a service context, so you could imagine this being what I'm talking about.
Oh, absolutely. Yeah. No, there's a lot of things. I mean, we have a lot of stuff in front of us in terms of what might be due next. With Naiad, we tried to build the system, the thing that could actually make it go, assuming you could actually tell it what to do.
Yes.
And that's sort of where we are now. And there's a lot of stuff you could totally imagine building on top of this. Moving this out to something like Azure, setting it up so that multiple people can actually use the same subcomputations. Instead of having everyone do their own Twitter graph analysis, everyone just taps into the exact same feed off of the results of the computation. And then they can do their own thing with it, but we've saved a tremendous amount of work by only having one instance of this iterative computation going on.
Awesome. And so it'll take a fair amount of RAM.
Oh yeah. No, it's that's one of the things that we're working on engineering. But the main limitation of Naiad at the moment is that the bigger and bigger data sets you get, the more memory you're going to need, which is why you want the more computers. It turns out getting more computers makes it go faster in some parts of the computation, but these low latency aspects, you don't really need 1,000 computers to make this millisecond response time. This is because the change was so small. The memory is definitely exciting, and we'll see how that goes and how that really ties our hands. We're definitely not targeting at the moment terabyte plus data sets, but generally smaller, more reduced data sets. So you've analyzed your web corpus, you've actually extracted the hyperlinks, you've thrown away the leaves that point to nothing in particular, and now you've gotten yourself down to a few gigs or so of graph data.
Interesting. But I mean, once we solve the problem, once you think of like cloud RAM, like endless amounts of memory.
That'd be nice, yeah.
That would be a great thing, because this is like one giant state machine.
Yeah.
Right? It's a super complex, brilliant work you guys have done, but in essence, that's what it is, right?
Yeah. It's basically keeping a whole bunch of different indexed relations up in memory, so that when you think that you want to change one of them, you can leap immediately to that point. And if stuff's not in memory, that's going to be slow. If stuff's in memory, it's delightful. It's a little weird that if stuff's in memory, but it's in a different data center or something like that. That's not great. So there's still some limits, but absolutely, if someone had a big data center, they decide this is going to be the compute engine for this sort of thing, and we'll share all those resources between everyone who wants to use it. It definitely seems a lot better than forcing everyone to go out and get their own terabyte of memory or something like that.
Totally. Well, someday maybe it'll be like a cloud NUMA kind of thing.
No, I mean, the future is very exciting in this
totally.
regard.
Hey, so there's a lot of smart people on Channel 9. I'm talking to you people out there. download this. You can see the link right under the player. Start playing around with this and give some feedback. And I'm sure Frank would be happy to engage.
Absolutely. No, we're very excited to see what people want to do with this, what sorts of things we've screwed up. We've certainly made some compromises, and we'd love to know that was a total error, or it's really easy to fix, and we'll just fix it, and
right on.
You can have what you want.
Cool. Well, hey, thank you.
Oh, no, of course, happy to.
And great work, man.
Thanks.
Cheers.